All right, so as I was talking about in the last video, this is the picture of the HR diagram. Again, I know I just said this, but luminosity is along the vertical axis and temperature is along the horizontal axis. But it's kind of the reverse, like if you, anytime you've ever had, axes, the numbers usually increase as you get further from the origin. As far as temperature goes, it's backwards. Okay, so the higher temperature is close to the, where the x and y axis would cross, also known as the origin. So you got really high temperatures here, and then as you get further down the line, the temperatures get cooler. So these are O stars over here, and these are M stars over here. All right, so let's continue with this thing. I mean, it's a remarkable tool, and it was a great discovery. It's basically a picture into the evolution of a star. That's what this thing is. All right, so three main parts of the HR that you find in the HR diagram. All right, let me mention this. So this kind of almost diagonal line. It's not quite a straight line, but this is called the main sequence. And this is by far where the vast majority of stars are found along the main sequence. These are stars that are undergoing, they're just, they're normal converting hydrogen into helium. Okay, stars that are way up here are much hotter, much more luminous than stars down here. I'll talk a little bit more about that later. And then, as a star leaves the main sequence, it goes up into this region here. These stars are called the giant stars. So that's the general classification of these stars. There are different types of giant stars, but there's red giants, there's blue giants. Anyhow, these are giant stars, and then after they've gone after a star has undergone the giant, it is really towards the end of the star's life. The stars will end up way down here in a region called the white dwarfs. So these are very, very small stars. In fact, the very first one that we ever found was in a binary system. The bright star Sirius that you look up in the winter sky, just to the left of the belt of Orion. It's actually a binary star, and Sirius B was the first one to be discovered. And it turns out that Sirius B is a white dwarf. All right, we'll have a lot more to say on that as we get more into stellar evolution. Remember, this chapter 13, is all about really the tools that we use to understand the stars, understand what's going on with stellar evolution. All right, so this is a little bit more, so you can see, there's the O stars and the M stars. They're just, it's the same axis. It's just down here it's showing temperature. Up here it's just showing the stellar classification. Notice the stars that are the exact same luminosity as the sun. Of course, the sun, you would draw a line right there, and there's the sun. There's and drop a straight line down, and the temperature of the sun is right at 6,000 Kelvin. Notice the white dwarfs are extremely hot, but they are not very luminous. In fact, some of them are only a tenth or even 100th, or even 1,000th the luminosity of the sun. And that really comes to, or our understanding of that is actually quite simple. If you take a star like Sirius B right here, okay. If we go straight up and on the main sequence, we find stars that are somewhere greater than 10,000 times the luminosity of the sun, and yet Sirius B is less than 1/100th the luminosity of the sun. How could that be possible? How could the two stars be exactly the same temperature? Okay, so you just draw a vertical line, right? So here's the temperature. I'm not drawing a very good vertical line, so you just go straight up, and the two stars, the stars in the main sequence right here, and the stars that are white dwarfs right here, have the exact same temperature. So it's somewhere greater than 20,000 Kelvin. Probably about 23,000 or something like that. It doesn't matter what it is, but anyhow, they both have the same temperature. How can they possibly have different luminosities? And the answer is a very simple answer. The only way that these two stars could have different temperatures, the same temperature but different luminosities. So they're putting out the ones way up here are putting out a whole lot more power than the ones down here, is just simply size. That's it. Size is the difference. These stars are much, much bigger, and that's why these ones down here are called dwarf stars. They're very, very tiny. All right. So again, the main sequence, this region right here, the sun will stay on the main sequence it's been on there for billions and billions of years. About 4 billion years. It's going to be on there for at least another 4 billion years. But keep in mind, 3 general parts of the HR diagram: the main sequence, the giant stars, and the white dwarfs. All right. This is kind of just saying the same thing that I just mentioned. Just looking at it in a little bit more detail. So, like, stars along these lines would have the exact same, these along this line right here, they would be 1/10 the size of the sun. These stars right here would all be 1/100th the size of the sun. These would all be the same size. These would be 10 times. These would be 100 times. These would be 1,000 times the size of the sun. All right. Anyhow, and notice the masses of these main sequence stars. There's actually a relationship between the mass and the luminosity as long as a star is along the main sequence. So these stars way up here on the main sequence are anywhere from 20 to 30 times the mass of the sun, and then it goes down, and then you get to the mass of the sun, and then stars below the sun on the main sequence are smaller than they have less mass. Like, for example, Proxima Centauri, Barnard's star, another star that has less. I mean, there's lots and lots of stars. In fact, most of the stars in the galaxy are down in this range right here. They're tiny stars. All right, let's see. So notice typical densities of main sequence stars are about 1 gram per cubic centimeter, roughly the same as the sun. The sun's a little bit more dense than that. But notice for the giant stars, it's about 10 to the minus 6 grams per cubic centimeter. There's that mass luminosity relationship. So that comes from the main sequence. We're not actually going to use this equation directly, but it's good to know that if you know the absolute luminosity, you can predict what the mass of a star is. And then, of course, if it's a star that's in a binary system, you can go and measure the mass of the star using the modified version of Kepler's third law. All right, let's see. I think I already covered this. All right, you're just subdividing the giant stars. That's not that important to us. Just remember, main sequence. I know I've already said this stuff, but main sequence stars. These are really luminous stars up here, more massive, and then you go down, and there's the sun, of course, and then there's stars down here on the main sequence that are less massive than the sun and less luminous than the sun. Then you get the giant stars, and then after the giant stars, after that phase, they go down and become white dwarfs. At least some of them become white dwarfs. We got a whole chapter on that. That's all about what's called stellar evolution. Yeah. So I just covered all that. Let's see, keep going. All right, so variable stars. Let me see if I can cover the so there's generally there are many different variable stars, but there's three main types. Okay, so there's the one type that we knew about originally is called a Cepheid variable. It has to do with the type of star that's called a Cepheid variable. But there's many Cepheid variables. It doesn't have to be in the constellation Cephus. And then there's variable stars vary their brightness. It's as simple as that. And they do it in a periodic way. So Mira variables are very long variable stars. So usually hundreds and hundreds of days for their brightness to vary. Cepheid variables are stars that vary in brightness over a period of days. Okay, so generally less than about a week. Not all the same period, but so there's that those middle variable stars are called Cepheid variables. The long variable stars are called Mira, and then there's the last one is called RR Lyra variables. All right, let's see. Oh, there they are, right there. So they're in this region called the instability strip. All the variable stars are in this region called the instability strip. What that strip is when the star is towards the end of its life, leaving the main sequence, it enters this region and varies. The RR Lyras are the shortest variable stars. These things vary in a period of hours. All right. Now, what's important about these variable stars? It turns out that they are used to measure distance. Right. So that's why, and we can even use these to measure galactic distances. Okay. So even stars outside of our galaxy are, we find Cepheid variables in other galaxies out there in the universe, and the thing about it is they vary, and when they vary, we can measure that. We can measure how much time they take to vary, and because of that, and because of this equation that I'm showing you here is if we know the variability, and we measure the brightness, we can figure out how far away they are. That's how this works. Okay, so we're not going to use this equation in this chapter. We will use it later when we talk about galaxies. So that is expanding this method of standard candles using variable stars. Right. So the Mira variables, the long variable stars, the Cepheid variables, the medium one, and then RR Lyra. All right, so let's see. Yep, I think that'll be about it. All right, so I'll start with chapter 14 in the next video.